is there a way to draw a rectangle with an area of 16 where one of the side lengths is 0? So it is not physically possible for there to be a rectangle with a length or a width of 0 because anything times 0 is in fact 0. So what would happen, like, if your area is still 16, what would happen if your width got really, really, really long?
Your length got really short.
Yeah, your length would just get really, really short. But would it ever get to 0?
No.
No, it would just keep getting, like, as it got bigger, like, width-wise, it would just keep getting smaller and smaller and smaller length-wise. Opposite would be true. If it got smaller width-wise, it would just keep getting taller and taller and taller to maintain that area of 16. And you can see that in the rectangles that you drew, because, like, the first one you drew was, like, really tall. And then the next one you drew was, like, kind of medium size. And then you drew one that was even. And then you drew one that was, they started alternating. So there's other rectangles you could draw in there. These are just the only ones that happen to be nice, pretty, like, whole numbers. But that doesn't mean you couldn't have decimals, you couldn't have fractions. But what would be true every single time about these points? They would touch the line. And what happens when you multiply that x and that y value together? It was 16 every single time. So that's consistently true. And that's where we got that idea of indirect variation, that every time you multiplied those pieces together, it consistently gave you the same number. So what this graph is, and this is the next type of function we're learning about, it is called a rational function. So we are talking about rational functions. Do y'all remember what the word rational means? Fractional. It's exactly what it means. So everything that we're going to be dealing with for the next 3 weeks are going to be fractions. Yay! But they have variables in the denominator, and that's what's going to make things complicated. We're going to learn how to graph them. We're going to learn how to add them, subtract them, which I'm going to tell you, adding and subtracting is going to be tough because we're going to have to get common denominators. And then we're also going to have to learn how to multiply and divide them. Multiplying and dividing is so easy. Oh, it's so wonderful. You will like multiplying and dividing. But before we can do any of that, guess what we have to do first to all these functions? Factor. And you know how to factor, right? Yay, you know how to factor. Oh, you know how to factor. So factoring is like the premise. It's the first step to actually doing anything with rational functions. And I've been telling y'all from day one that if you couldn't factor, you wouldn't be able to do all the other stuff. This is kind of where we're starting to get into that. That if you can't factor, then you're not going to be able to do rational functions, which you all can factor, so we don't have to worry about that. Okay. If we were to graph the function 1 over x, that's what this graph is here. I've already graphed it for us in Desmos. I just put it in there because I was like, it's easier if I do it myself. So this is the function f of x equals 1 over x. If you don't believe me, you can graph it, but I promise it is. So what are some observations you have about this graph?
There's a positive and a negative.
Okay, there's a positive and a negative side. What else you got for me? Okay, so there are two curves, not lines, two curves. Then they never meet. What happens as they approach the y-axis?
They get close, but they don't touch.
They get close, but they never touch. So like on this side, there is. On this side, they're getting close over here, and they're getting close on the negative side. And what's going to happen is they're going to keep getting closer and closer and closer and closer and closer to 0, but it's never going to touch 0. The same idea with our rectangle is that as we made our length bigger and 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 bigger this way, then what happened the other direction? It gets smaller. But can it ever be 0? No, because we can't. If we multiply by 0, then we don't have a rectangle anymore. We just have like something that's straight. We just have a line.
So we're not going to have any x or y intercepts?
On this graph, the way it is at the moment, the parent function, 1 over x, there are no x and y intercepts. That does not mean there won't be, because when we start shifting stuff, like if I were to move this graph up, would it cross the y-axis? Yes, and if I were to move it left or right, it would cross the x-axis or the y-axis, one of the two. If I move it up, it would cross the x-axis, not the y-axis. Is that what you're saying? Gabriel? Is that what you were saying?
No, I was saying like that because like once I have my calculator and it annoyed me because 0 was like error.
Oh, yes. Okay, so it is an error. Why is that an error if you plug in 0 for x here? That brings up a good question. Can you try that? If you plug in 0 for x, it says error.
Because 1 divided by 0 is nothing.
1 divided by 0 is nothing. It's called undefined. Okay? So that's where that comes from. So what about end behavior? End behavior. End behavior we learned was we started writing like as f of x approaches positive infinity. So I'm looking at the right end of my graph. Well, if we keep following this right end and following this right end and following this right end, what do you think is going to happen? We're going to get to that in a second. What's going to happen is it continues to go out towards positive infinity. What happens to my graph? Thoughts? Do what? That's a good question. Does it stop? When we look at this graph, what happens to our end behaviors, and we're going to talk about this again in a second, is we say that as f of x approaches positive, or sorry, that should not say f of x. That should just say x. Let me try that again. We would say as x approaches positive infinity, we say that f of x approaches 0. Because that number just keeps getting smaller and smaller and smaller and smaller and smaller. But it approaches 0 from the positive side, which means that it's getting closer and closer and closer to the x-axis, but it's above the x-axis. Okay? And then if we look at our other end behavior, what's happening out here when we follow the right end of the graph? The left end, sorry. It's approaching 0 from the negative side. It's just getting smaller and smaller and smaller and smaller and smaller. So we would say as x approaches negative infinity, f of x approaches 0 from the negative side. And again, that's just because someone in first grade will go, well, 0 is not positive or negative. You're right. We're not saying 0 is positive or negative. We're saying it's getting really close to 0, but it's on the negative side. So it's from the negative numbers. Okay? So if we look at this graph, we can see that it never hits 0. So the reason why is there's these invisible barriers. So we have these two asymptotes, and every graph has them, well, for the most part. Sometimes they don't have horizontals, and we're going to talk about why. We'll get to that, later. That's not today. For today, the basic ones that we're dealing with, they all have a horizontal and a vertical asymptote. So now here's my question for you. Do you think that the y-axis and the x-axis are always asymptotes? Why not?
Could be a number.
Why could it be a number? Not saying you're wrong. I'm asking, what would have to happen in order for it to be a number instead of an x-axis?
Graph up and down or side to side is going to cross.
There we go, when we shift our graphs. Well, guess what else we're talking about today? Transformations. Because we can. Yes, we have to. Okay, so we're going to talk about transformations in a minute. Let's talk about just our basic parent function a little bit. My domain. Domain, is that my x's or my y's? X's. Okay. Thinking about what we talked about a second ago. What's the only thing in the world that x cannot be in this function? 0. So the way we write that, well, we say, first of all, that the domain is all real numbers except 0. That was a terrible 0. Except 0. I'm on the very first page of the notes. 9.2. What page is 9.2? 469. There we go. So the function accepts all real numbers except 0 because division by 0 is undefined. So the domain in inequality notation would be x's that are less than 0 or x's that are greater than 0. It could be either one. It can't be both because you can't have a number that's less than 0 and greater than 0. That's not mathematically possible. So we use the word or in there. In interval notation, we use this symbol called U. And that U is a union symbol. And we would say that our domain goes from negative infinity to 0, union 0 to infinity. What symbols are here in the middle next to U? What are these? Right here. This is not a complicated question, sorry. There are parentheses. What else could we potentially use there? Brackets. When do we use brackets?
When it's less than or equal to?
Yes, when it's equal to, when we can be that number. We can't be 0. It can't be 0 because we can't divide by 0. So we have to use brackets here. Now, set notation, y'all didn't like set notation for the first part of the year. It was not your default reaction because it was complicated. But set notation is really easy when it comes to stuff like this because all we say is that our domain is all x's such that x cannot be 0. It's x's such that x cannot equal 0. And that's true because x can't be 0. X can be anything else we want it to be. It just can't be 0. Behavior, we would say, and we already said this a second ago. We talked about this when we looked at our graph. We said as x approaches positive infinity, let me just draw a graph real quick here so we can remember what that looks like. So x-axis, y-axis, graph, and graph. Okay, there we go. All right, so there's roughly a sketch of my graph. That's what all rational functions generically take the shape of. As x approaches positive infinity, that is the right end of my graph. Where's the right end of my graph going? Do y'all remember?
To 0.
To 0, and it's approaching 0 from the positive side. Okay. And then as x approaches negative infinity, that's the left end of my graph. And what's happening to the left end of my graph? 0 from the negative side. So that means it's approaching 0. It's getting closer and closer and closer to the x-axis on the bottom side of the graph. That's all that means. The positive side of 0 means it's above the x-axis. The negative side of 0 means it's below the x-axis. That's what those two things mean. Okay. It asks us to state the range. So the range, well, think about your y's. What can that function 1 over x, what could it never equal? 0. So it's all real numbers except 0. So we said that the range would be y's that are less than 0 or greater than 0. Can be either one. And then in set notation, we say it's y such that y cannot equal 0. Which just means, again, that y can be any number we want it to be except for 0. That's the only thing it can't be. Same idea in interval notation, negative infinity to 0, union 0 to infinity, and those are in parentheses and not brackets. About what A does to the graph. What does A do to the graph? It's vertical stretch or compression. How do you know if it's vertical versus horizontal?
If it's inside the parentheses.
Yes, its location, inside or outside the parentheses. So A is vertical stretch or compression. Okay, what about B?
Horizontal stretch.
It's horizontal. We know it's horizontal because it's inside. It's horizontal stretch or compression. What's important about B here? It's the reciprocal or the refliprical. So we flip that fraction. Okay, what about the C? What does C do to the graph? It shifts it left or right. And again, that's got to be the opposite of what we think it should be. And then plus D here on the outside, what's that going to do?
Up and down.
It's going to shift the graph up and down. So the only difference is instead of parentheses, we're going to see fractions. So for rational functions, all this stuff that's inside, let me do this. This isn't going to be inside parentheses. This is going to be in the denominator. So we're looking to see, is it in the denominator or not in the denominator? If it's in the denominator, that means it's horizontal. And again, I'll give you this rational functions reference page tomorrow. All right, so part A. We're supposed to predict the effect of the parameter on the graph. So we have g of x equals 1 over x minus 3. So where is that minus 3 at? It's the denominator. It's in the denominator. It's like C. So that's going to shift the graph either left or right. So what's a minus 3 going to do to the graph?
Right.
Okay, it's going to move it to the right 3 units. Okay, for part B, the graph of g of x equals 1 over x plus 3. So what is that plus 3 in the denominator going to do? Left 3 units. So part D on the next page, we have 1 over x and then the whole thing plus 3, and then 1 over x and the whole thing minus 3. So what is this plus 3 going to do that's on the outside? It's going to move the graph up 3. And what about this minus 3 here? What's it going to do? Okay. Look at part C. Okay, in part C, where are all of our numbers here? The outside. So they're not in the denominator, they're on the outside. So what are all those numbers going to do? Vertically stretch or compress. And those are normal. So what is 2? If I multiply something by 2, am I vertically stretching or vertically compressing the graph? Stretching. So vertical stretch of 2. Okay, what about 1/2? Or 0.5, because 0.5 is the same thing as 1/2. So what is that going to do to the graph? Vertical compression of 1/2. Okay, what's different about C and D? There's going to be a reflection because it's a negative sign as well. So the 0.5 is still going to be a vertical compression of 1/2. But the negative sign itself, what is that negative sign that's on the outside going to do? Reflect over the x-axis, sorry. It's going to cross over the x-axis. Yeah, it's going to change all your y's. It's going to make what y's were positive, negative, and what y's were negative, it's going to make them positive.
Is the y or the x's?
It's flipping over the x-axis, but it's changing the y values. Okay, same thing with the next one. This negative sign here is going to reflect across the x-axis. Look, I used one of their blanks and made a complete sentence. And I'm so proud of myself. Okay. All right, so the last part, part D, all of those numbers, where do you see them?
There's one next to the x. What's going on?
They're technically on the inside because we said for our rational functions, we weren't looking at the inside, we were looking at the denominator, the bottom. So that 0.5x is like saying it's inside the parentheses. Okay, so 0.5x, what is that going to do to the graph? It's a horizontal stretch by a factor of what? 2. Why 2 and not 0.5? Yes, we have to remember the reciprocal. The reciprocal, okay? So what about 1 over 2x? It's a horizontal compression of 1/2. Okay, what happens when you throw a negative sign in there? Whenever you throw that negative sign in, that reflects over the y-axis. So that's going to be true for both of the last two. And I'm not going to fill in the stretches and compressions on those last two because I think you can figure that out. Okay? It's the same as the first two. You just go back and look at the first two. They're the same thing. All right, so we're on page 275, and I have the function 1 over 2 times x plus 3 minus 1. So let's start with the minus 1. What's that going to do to the graph?
Down 1?
Down.
It's going to end up moving it down 1 unit. Oh, it's okay. All right, why does that minus 1 move it down?
Outside.
It'd be outside. It's where D is in this case. Okay? All right, what about the plus 3 in the denominator? What is that going to do? Left 3. And lastly, what about our 2 here? What's that going to do?
It's a horizontal stretch
horizontal compression of.
It's a horizontal compression of 1/2.
So where would the number be for A?
If it was A, okay, it would be, yeah, it'd be like on the outside. So if you had A, it would be like, just making this up, g of x equals 3 times 1 over x minus 4 plus 2.
So it's like those fractions, what do you call those? Mixed fractions.
Yeah, so it could be here, or it could also be here on top. Either one would be the same thing, and that would be a vertical stretch or compression. Okay? Great question there. Okay, so let's talk about what's going to happen if we shift our graph. So here would be our graph. What happened is we translated it.
Yes.
Okay? It did what?
Curvy.
They still have an asymptote.
It still has asymptotes. This time, though, where are my asymptotes? There's, which kind of asymptote is it? -3.
The vertical one.
The vertical asymptote. So there's an asymptote here at -3. So that'd be our vertical asymptote. At the equation would be x equals -3. And there's also one at -1. So thinking about these numbers that we had, compare those to what we just said about our asymptotes.
Oh, those are the asymptotes.
They're the same. So the -3, like, or this 3 that shifted the graph left 3, which asymptote did that affect?
The Y.
The vertical one. Vertical asymptote is going to be affected by horizontal shifts. So this is going to be a very confusing idea, okay? Just this idea of the horizontal shifts changing the vertical asymptotes, okay? That's going to be a very weird idea. It makes sense when you think about it, but just those words, they're going to be conflicting a lot. So you have to be intentional about remembering that. When you shift something that's vertical, you can't move something that's already vertical. You can't move it more vertical. You can only move it horizontally, okay? So we shifted it to the left 3 units, so that means our horizontal asymptote became x equals -3, and that's because of that +3 in our denominator. And then our horizontal asymptotes, so the ones that look like this, they can't move horizontally, they can only move vertically. So that's affected by our vertical shifts. And that equation would be y equals -1. And again, that has to do with this -1 here, that that translation up or down, that shift up or down.
So it's C and the D's.
C and D are going to affect your asymptotes.
Isn't that a point too?
It is not a point on the graph. I mean, it's where the asymptotes intersect, but it's not actually a point on the graph.